To build on our library of known identities, we'll add the sum and difference identities for sine and tangent here in section 3.4. Let's begin with the sign of a sum or a difference. In order to learn all these detailed identities, it certainly helps to compare and contrast the formulas. For that reason, let's go ahead and record the sum and difference identities that we already know for cosine. Cosine of alpha plus beta, as we have learned, is equal to cosine of alpha times cosine of beta minus sine of alpha times sine of beta. Similarly, cosine of a difference, that is alpha minus beta, is equal to cosine of alpha times cosine of beta plus sine of alpha sine of beta. Now, the sign of a sum or difference formulas are going to look very similar. So let me take the opportunity to point out a simple pattern and a way of remembering at least the sign patterns in this identity. For cosine of a sum, notice if we have a plus in the argument position, that translates into a minus in the expanded position. I like to remember that cosine starts with a C, and that reminds me to change the sign. Change starts with a C. Similarly, if we have a minus in the argument position, that's going to translate into a plus in the expanded position. And once again, cosine starts with a C, and that reminds me to change the sign. Now let's consider the sign of a sum or a difference, and we're going to prove both of these formulas. To begin with, sine of alpha plus beta can be expanded as sine of alpha cosine of beta plus cosine of alpha sine of beta. Notice the pattern in the functions. We have sine times cosine plus cosine times sine. In our cosine formulas, the cosine repeats for the first term and the sine repeats for the second term. That's true for both of those identities. What we're going to see with sine of a sum and difference is they have a similar pattern, but they're distinct from our cosine formulas. Similarly, sine of alpha minus beta can be expanded as sine of alpha times cosine of beta minus cosine of alpha sine of beta. While the functions alternate, that is sine times cosine, cosine times sine, notice the angles remain in the same order, alpha, beta, alpha, beta. Also observe that when we have a plus between the angles of the argument of a sine function, this becomes a plus in the expanded form. Sine starts with S, and that reminds me to keep the sign the same. Same starts with S. We can see that over here as well. When we have a minus between the angles in the argument position, we also have a minus between the terms in the expanded formula. Sine starts with an S, same starts with an S. As you learn all of these identities, compare and contrast, and look for those overall universal patterns. That will help you to remember them. Let's go ahead and prove the sign of a sum identity. If you'll recall, when we first constructed the proof for the cosine of a sum, it was pretty complicated. We had the diagram of the circle, we were looking at chords and angles, and it was very involved. But once we have that basic proof, then all of our other proofs can stand on that strong foundation. We're going to do this proof in a very efficient way by building on formulas that we already know. In order to prove this identity, sine of alpha plus beta, I'm going to write it in terms of its cofunction. The cofunction would be cosine of pi over 2 minus the angle. The angle here is alpha plus beta. Then we can go ahead and distribute the negative in the argument to obtain cosine of pi over 2 minus alpha minus beta. Now I'm simply going to imply a shift in the order of operations here by grouping this pi over 2 minus alpha together. We'll call that our first angle, and our second angle is minus beta. Now the point of doing that is now I have cosine of a difference. Cosine of this first angle, pi over 2 minus alpha, and the second angle there is beta. So we can go ahead and apply an identity that we already know, cosine of a difference. Now I'm going to scoot over to the left a little bit just to take advantage of some workspace. So we'll expand this as cosine of the first angle, pi over 2 minus alpha, times cosine of the second angle beta. And remember, in the cosine of a difference, we're going to change the sign to plus sine of the first angle, pi over 2 minus alpha, times sine of the second angle beta. Then you can spot our cofunction identities. Notice the first factor, cosine of pi over 2 minus alpha, that's equivalent to sine of alpha. So we have sine of alpha times cosine of beta, plus then once again applying our cofunction identity, sine of pi over 2 minus alpha is cosine of alpha times sine of beta. So that establishes this identity. Now we could do something similar for the proof of sine of alpha minus beta, but now that this formula has been established, we can build other proofs on this verified identity. That's what we're going to attempt for the proof of sine of a difference. Let's simply rewrite sine of alpha minus beta as sine of alpha plus negative beta. Now we have disguised sine of a difference in terms of sine of a sum, and that's good because we have a formula for sine of a sum. Let's go ahead and expand this according to our sine of a sum identity. We'll find sine of the first angle alpha times cosine of the second angle, which is negative beta. And remember, in the sine of a sum, we keep the same sign between the terms. Cosine of alpha times sine of negative beta. These are a little different than the cosine of a sum or difference identities because remember, we're alternating the functions sine, cosine, cosine, sine, and we're keeping the angles in the same order. In this case, alpha, negative beta, alpha, negative beta. Now we can use our even and odd identities to simplify. Recall that cosine is an even function, so cosine of negative beta is equivalent to cosine of beta. Similarly, sine is an odd function, so sine of negative beta equals negative sine of beta. But we can filter that negative all the way to the left of this term, and essentially it's going to change the sign in between. So we end up with the verification for the sine of a difference identity. Notice that we built the proof for the sine of a difference formula on the previously established formula sine of a sum. We built the sine of a sum formula on a previously established cofunction identity. So all of these identities work together to establish all of these interesting relationships between our trig function. Let's look at how we might use these formulas in a calculation. In example 1, we want to find the exact value of the trig function. This means we want to evaluate it without approximation or rounding. So we can attempt to express the argument as either the sum or difference of two common angles on the unit circle. Notice 11 pi over 12 is not a common angle on the unit circle. So we need to learn how to express this as either a sum or a difference. So I'm going to start with the sum because that's generally a little bit easier. Now, we may look at that, and since it's in radians, our brains kind of go a little slower in radians, so what are we going to do? Well, I notice the denominator is a 12, so I'm just going to experiment. I'm going to take some angle on the unit circle, maybe 3 pi over 4, and I'm going to add it to pi over 3, okay? And the reason I'm doing that, I'm just picking two angles at random that would require a common denominator of 12. Okay, notice if we multiply that first denominator by 3, we will obtain the 12, so I need to multiply the first numerator by 3. And then second, we need to multiply this denominator by 4 to get 12, so we'll multiply the numerator by 4. Now, when I add these together, I missed the mark, right? Now, I'm pointing this out because sometimes it takes a little bit of trial and error and experimentation before you find the right combination. But persevere, keep working with it until you find the right combination. Let's try another possibility. How about pi over 4 and 2 pi over 3? These would also require a common denominator of 12. Looks like our common factor for the top and bottom of that first fraction is 3, and the common factor for the top and bottom of the second fraction is 4. 8 pi plus 3 pi over 12, that's going to give me the 11 pi over 12 that I'm looking for. So that's our winning combination. We can now express sine of 11 pi over 12 as sine of a sum pi over 4 plus 2 pi over 3. Another way to execute those calculations is simply to convert pi over 12 to degrees and then find a sum or difference in degrees. Sometimes that's a little easier. Okay, I'm out of workspace, so I'm going to continue this down here. Let's go ahead and expand our sine of a sum formula. Remember, the functions alternate sine, cosine, cosine, sine, but we keep the angles in the same order. And for the expansion of sine of a sum, we keep the same sign in between. So we have sine of the first angle pi over 4 times cosine of the second, 2 pi over 3. Same sign here. Cosine of the first angle pi over 4 times sine of the second, which is 2 pi over 3. Let's go ahead and evaluate those functions. Sine of pi over 4 is the square root of 2 over 2. Cosine of 2 pi over 3 is negative 1/2. Cosine of pi over 4 is the square root of 2 over 2. And sine of 2 pi over 3 is the square root of 3 over 2. Notice we're going to get a common denominator there of 4, so I'm going to go ahead and combine my fractions into a single fraction. And I'm going to lead with the positive term in the numerator. So square root of 2 times square root of 3 gives us square root of 6. Square root of 2 times negative 1 gives us negative square root of 2. So the exact value for sine of 11 pi over 12 then is the square root of 6 minus the square root of 2 over 4. Now that was a lot of calculations, a lot of potential for error. So I am going to go ahead and verify this with my calculator. First thing I want to do is make sure that I am in radian mode. So I'm going to make that switch. And then I'm going to evaluate the original problem. That's sine of 11 pi over 12. Now, I'm not really interested in the decimal output other than for comparison with the answer that we came up with. I want to make sure that our answer yields the same decimal approximation. Be careful how you type this in. You want to make sure, whoops, try that again. You want to make sure and include the operation in the numerator in a set of parentheses. So we have square root of 6 minus square root of 2, all divided by 4, and we come up with the same decimal approximation. So this indicates that our exact representation of sine of 11 pi over 12 is correct because the decimal approximations are the same. We're not interested in reporting the decimal approximation because remember, the problem says give an exact value, but we can certainly work our way around that in order to check our answer. That's always a good idea on a test. Now, our next example is in degrees, and that's good news because degrees are sometimes easier to find sums or differences for. Now, on the previous problem, we did the sine of a sum formula. So let's practice sine of a difference on this problem. 75 degrees can be obtained by taking 120 degrees minus 45 degrees. Remember, I'm striving to use angles, common angles from our unit circle to re-express these non-common angles so that we can evaluate them exactly. Let's go ahead and expand our formula. We have sine of the first angle times cosine of the second angle. Now that's just 45 degrees, not negative 45 degrees, because remember this sign indicates we're going to keep the same sign in between our two terms here. Cosine of 120 is next in the formula, and then we finish with sine of 45 degrees. So sine of 120 degrees is the square root of 3 over 2. Cosine of 45 is square root of 2 over 2. Hope you're doing well on your unit circle values. Cosine of negative 120, or cosine of 120, is going to give me negative 1/2. And sine of 45 is the square root of 2 over 2. So once again, we have a common denominator of 4. I'm going to lead with the positive term, square root of 6. Oh, and they're both positive, right? Because negative times negative gives me positive square root of 2. But before we continue, let's go ahead and verify that with our calculator. Now, this one's in degrees, so I'm going to go ahead and make the switch to degree mode. And then I'm going to check two things, the original problem, which was sine of 75 degrees, and my final answer. Remember, numerator, if it's got an operation, needs to be enclosed in a set of parentheses. So we'll type in square root of 6 plus the square root of 2 and divide that by 4 and hope for the best. Yay, we did a good job. Okay, so you need to be able to evaluate these exactly, but also check them with your calculator for accuracy. Now, by the way, there's multiple ways to work this problem. We opted for sine of a difference, but notice you could also evaluate this using sine of a sum formula if you expressed it sine of 30 plus 45 degrees. That would yield the same result. All right, let's apply these formulas in reverse and see if we can recognize the pattern. In example 2, we want to simplify each expression. Notice the pattern, sine, cosine, cosine, sine. Also observe the angles are in the same order. 5, 10, 5, 10. So this is matching the pattern of our sine of a sum or difference formulas, right? But what we're going to recognize is in the sine formulas, the sine here is the same as the sine in between the two angles in the argument. So we could write this as sine of 5 degrees plus 10 degrees, which of course simplifies to sine of 15 degrees. But you know what? Let's not stop there, because we can take this all the way down to the evaluation for this particular problem, because we could rewrite 15 degrees in terms of the difference of two common angles. So we can go ahead and evaluate this one as sine of 45 degrees minus 30 degrees. Let's expand that with our sine of a difference formula. That is sine of the first angle 45 times cosine of the second angle 30. Keep the same sign in between, and then we have cosine of 45 degrees times sine of 30 degrees. Those are pretty easy angles to work with because they're both quadrant 1 angles. Sine of 45 degrees is the square root of 2 over 2. Cosine of 30 is square root of 3 over 2. Cosine of 45 is square root of 2 over 2. And sine of 30 is 1/2. So this gives us square root of 6 minus the square root of 2 over 4. Now remember, you can check that with your calculator and you find out that's the correct value. Let's try example B. Looking at the pattern, we have sine, cosine. We can just simply reverse those and then we'll have the order cosine sine. Also, we can evaluate these negatives in the argument using our even and odd identities. So let's work on both of those things. Because sine is odd, sine of negative 11 degrees can be written as negative sine of 11 degrees. Because cosine is even, cosine of negative 51 can be written as cosine of 51 degrees. Sine of 51, no change necessary there. Cosine of negative 11 can be written cosine of positive 11, since cosine is even. Now, in the two formulas that we're considering in this section, neither of them started with a negative term. So let's go ahead and reverse these two terms, and let's reverse these two factors. Actually, when we switch the two terms, it's those two factors that we'll need to reverse. So starting with this one, we have sine of 51 degrees times cosine of 11 degrees minus, switching our two factors, cosine of 51 degrees sine of 11 degrees. Now you can see we have the pattern sine, cosine, cosine, sine. The angles are in the proper order, 51, 11, 51, 11. So we can recognize this now as sine of a difference. And remember, we know it's a difference because this is a negative sign. So we can condense this down to sine of 51 degrees minus 11 degrees. So that's going to give us sine of 40 degrees. Now, we won't be able to evaluate this one with a sum or difference of unit circle values, but we can certainly check it on the calculator. So I'm still in degree mode. What I want to do is begin by typing in the original problem without any changes. So we had sine of negative 11, cosine of negative 51. Make sure you close parentheses on all those arguments, times sine of 51, cosine of -11. So I'm looking at the original problem without making any changes in case I've made a mistake somewhere along the way. Then I'm going to evaluate our final answer, sine of 40, and we get the same decimal value. So that means we have simplified it correctly. We're only using those decimal values to check. That's certainly not the answer that I want to report. Okay, let's finish with example 3. Now we've done a problem like example 3 in the last few videos where we want to find the exact value of something like this. In this case, sine of alpha minus beta. Now, we don't either know alpha or beta, but we're given information about sine and cosine. Sine of alpha is square root of 3 over 2. Cosine of beta is square root of 2 over 2. And we know the locations of the angles. Alpha's in quadrant 2 and beta's in quadrant 1. Now, the last 2 times we worked a problem like this, one time around, we used the Pythagorean identity, sine squared plus cosine squared equals 1, to figure out cosine of alpha from sine of alpha, sine of beta from cosine of beta. Another time around, we used a graph of a right triangle and the definition of sine and cosine in terms of x, y, and r to evaluate the corresponding functions. But I'm going to give you one more option in this example. This one is special and unique because notice sine of alpha gives us a common unit circle ratio and sine of beta gives us a common unit circle ratio. So in this case, we're going to be able to figure out the angles alpha and beta. If alpha is in quadrant 2 and the value of sine is square root of 3 over 2, this means the reference angle must be 60 degrees. Because all the angles that have reference angles of 60 degrees have sine of either positive or negative square root of 3 over 2. Now, if alpha is in quadrant 2 with a reference angle of 60 degrees, we know it must be 120 degrees. So we know the value of alpha. Similarly, if beta is in quadrant 1, then it doesn't need a reference angle. If it's cosine of square root of 2 over 2, we know that goes with a 45-degree angle. So based on the fact that these have common unit circle ratios, we can actually solve for the angles in this case. Then we don't even need to expand our formula. We can say sine of alpha minus beta is sine of 120 minus 45. Well, we are going to have to expand the formula because if we find that difference, we would get sine of 75, which is not a unit circle value. But recall, up here, we've already calculated sine of 75 degrees. So we'll build on this work that we've already done. We've expanded it properly, and we can then report the answer. Since this is 75 degrees, we know that's equivalent to the square root of 6 plus the square root of 2 over 4. So that was a pretty efficient problem. Always be watching for those common unit circle angles. So at this point, we have a set of 4 sum and difference identities. We have 2 for cosine, and now we have 2 for sine. We'll add tangent to that list in the next video.